Okay, good morning. Uh, we are going to continue and I think finish chapter 14. So I think around next week or next 2 weeks, maybe we will have one with chapter 14, only for partial derivative. Maybe next 2 weeks, so you have time for study. Maybe Thursday. Thursday. Let me check the schedule first. So maybe November 30. Okay, maybe this will be quiz. Okay, so quiz, partial derivative. Okay. So you have time to study and at least two TA class. Okay, but then after that, we are going to have, I think from December 4 until 6, I will not be here. So Wednesday class is no class on December 6th. Let me write here. So December 6th, no class. Okay. And then we have regular class on Thursday, Friday, up until my goal is December 22nd. This will be a final exam on Friday. Okay, on Friday, hopefully we can finish chapter 15. So today I'm going to finish chapter 14 and maybe get small introduction to chapter 15. Okay. And I think for the quiz, for the partial drifting, I think that will be the last quiz in our course. And I think I still need to confirm your last makeup exam from your TA. I haven't checked, but my TA he will check first, and then I will check after that. Do you think it's okay? Your makeup exam, okay? Right? The question, okay. 1 hour, but I think should be able to solve most of it. Okay, so let us go back to this maximum minimum value. I think I mentioned last time the absolute maximum and minimum. It means that the difference is it has so aside from the function itself, it has the interval, and then to check which one is the absolute maximum or minimum, we need to check everything. So we need to check the critical points, check the value, and then check the value on the boundary, which means the interval. Okay, the interval. And then all the largest value will be the absolute maximum. The smallest value will be the minimum. Okay, so it's as simple as that. Okay. Maybe we could try this one, okay, just to make sure that we understand the steps. So to find the absolute maximum and minimum, first we start taking the critical points. Okay, how to take critical points? We are going to partially derive with respect to x. So this is 2x, negative 2y, right? And then take the partial y, which is negative 2x plus 2. And then take this both sides for partial x equals 0 and for partial y also equals 0. So since we have 2x equal to y or x equal y, we could substitute the left to right or right to left. But I think for the right part, we can definitely get that 2x is equal to x equal 1. So we can conclude that the critical point is 1, 1. Okay, so only 1 point, right? So critical point, only 1 point. Only 1, 1, like that. And the value, we check this point, we can check f1, 1. So we put back inside the equation. So 1 minus 2 plus 2 is also 1, right? But we have the rectangle. So we have the interval, which is described by this d. Okay. We could also express this d with the rectangle. So we can express d as x and y. So this is 3, 0. This is 0, 0. And y is until 2. So maybe here. This is 0, 2. So we have this rectangle. Okay. And this is the d. Okay. We take 0 to 3 for the x and then 0 to 2 for y. So we need to check the possibility of the maximum value from this part. Okay. So we are going to see that at least we have 4 segments. So 4 segments, 2, 3, 4. So we have 4 lines to get into the D. Okay. So we check on L1. So L1 is when the y is 0. The one that changes is x. Right? So this is y equals 0, right? So on L1, we can write y is 0. So fx 0, we can write like that. So everything with y will be 0, so this will be just equal to x squared. And we know that the x is from 0 to 3. Okay. So what's the minimum value? So minimum value for this L1, so minimum value is f00, which is equal to 0. Okay, on L1 only. Okay, and then we check another one on L2. We have x equal 3, right? X equal 3. On L2, we have x equal 3. So we can take into our equation 3y. So we are going to have 3 squared, 9, minus 6y plus 2y. Or we get 9 minus 4y. And since the y is from 0 to 2, oh, I forgot to write the maximum value, right? Let me write here. Maximum value for the first one, I forgot to write. Max value, since it is x squared, so it's going to increase, right? So the maximum value is when it is going to be 3, right? Or this is going to be 3, 0. So 3, 0, we check 9 minus 6, right? 3. Okay. Oh, wait, not 3, because the y is 0, so it's 9. Okay. Or maybe let me write maybe on here, make it a little bit smaller, and moving here, and then we can check the minimum value for the L2. We can check this will be 3, 2, right? Because it's 9 minus 4 multiplied by 2. It will be the minimum. So the minimum will be, this is 9 minus 8, 1. Okay, and then max value. So you need to analyze how the function will be from. Let's say we can imagine from the function itself. If the functions, for example, like this, it has like minus. So you could guess that the more y you have, then this function will be getting minimum. Right? For example, if you take 2 here, it's going to be very, very minimum. If we take 0, it will be its maximum value, right? Okay, you get the point. So it is always depend on the functions. Okay. So 3, 0, we take inside. It will be 9, right? And then let me make it resize this a little bit smaller, so to fit with this, maybe a little bit bigger. Okay, and then on L3 is that. Okay, so L3 is when y is equal to, so y equal to. So we have f x2. Fx2, it's become x squared minus 8, right? X squared minus 8. Or sorry, 2, oh, 4. X squared minus 4x. Okay. Plus 4. Okay. This is from 0 to 3 for x. And somehow we need to simplify it. So we have x minus 2 squared, which we can see that we have x equal 2 from this part to make it 0, or we can just try using the interval. Okay, so we take the minimum value. So minimum value is when it's equal 0, right? When it's equal 0, it means that f22 it'll be 4 minus 8, so minus 4 plus 4, it's 0. So this will be 0. Let me resize. And then the max value is f02. Because when x is 0, it will be 4. So 4.
let me resize this. Okay, and then one more line. We write here on line 4. Line 4 is on the y-axis. So it's x equals 0. So this will be f 0y. The functions become 0, 0, and then only 2y. So only 2y. This is y is from 0 to 2. And then we can just write the minimum value. Minimum value from here is obviously 0, and the maximum value is 4. Now from all this,
okay, so we have critical points, which is 1, 1. The critical point has value 1. And then we can check 1, is it maximum or minimum? We can compare. Okay? So we have the minimum value is 0. I think the minimum one from all of this is 0, right? So we can say the absolute minimum value is 0 when f is at 0, 0. And the maximum value it will be 9 when f is at 3, 0.
So we can check, we can conclude, we can make a conclusion from here. The absolute minimum is at 0, 0, and the value is, or maybe we'll write absolute minimum value is f0, 0 or f22, which is 0. So we have 2 points that makes absolute minimum, and then we can have absolute maximum. This is when at 3, 0, okay? Okay. So if you are given this kind of question,
so the first thing is finding critical points, and then check all the segmentation. Check all these segmentations. Usually it will be in a rectangle like that, so you can check first segment, second, third, and fourth. Check all the possibility of each point and look at the value. The minimum one will be the absolute minimum. The maximum one, the highest one will be the absolute maximum. Okay, so on the previous one, the previous section, we only care about the critical points. But now, since we have the restrictions on the interval, so we need to check the interval as well. Okay.
okay, now this is one method,
and to find the maximum minimum value for something like this, I think depends on the question. If the question is to just like find maximum value, you have the function, you have the rectangle, the interval. I think it should be easy to elaborate. I think the difficulty one is if we have like maybe the function a little bit complicated that you need to partially derive, and then make sure that your derivative is correct, and then you check the critical point, and check the rectangle, and then you get everything. So I think it depends on your ability to solve the derivative first, and then this identification observation. As long as you can get all this value, you will be able to see which one is the maximum and which one is the minimum. Now, aside from this maximum minimum value method, like we did before, like we have first derivative test, we have second derivative test, right? We have also
another method that which we call the Lagrange multipliers. This method is used for maximize or minimize a function, let's say a general function f x, y, z, okay, to a constraint. Let's say the constraint will be equal to k, like this. Okay. So what's the deal with this?
So we have a function. We have a function f. And then in another information, we have another function that equal to a constant, like this one. So whenever we have a function and a constant, it means that this function will be limited by this number, right? So the idea is actually, we are going to put this function f, and then we are going to fit the f onto g. So we are going to find a way to find how much f that when it's multiplied by something, it will equal to the g. That's the idea. So if we take the graph, let me put here. So this is the constraint. So the f, it can be equal to any constant, right? It can be equal to, like, for example, we have this all the numbers, and we'll have different level curve, right? different curve. But then we want to know if the f getting approach to this g when the g is equal to some k. So this is the g here. So of course it will somehow we get some point here. Okay. Now we want to know the point that is going to be minimized or maximized. Okay. So we are going to see how we can get how we can multiply this with some special multiplication symbols or multiplication variables, which we call the Lagrange multipliers. So it's why it's called the multiplier, because we want to multiply f with the g, or how much g to be multiplied with something to be equal to f. Okay? And we know from the previous part, where we have like this is it's like a tangent, right? This is like a tangent. So it means that the tangent at this point will be equal. But for the tangent in 3 dimensions, I think I mentioned this part I think last 2 weeks. The tangent is equal to the triangle, the inverted triangle, right? The del, the gradient triangle. Then we are going to use that. So the gradient for f equal gradient of g multiplied with something, and that's something we call the Lagrange. Okay?
So let me write here the method. So it's
I think a lot of words, but the important one is this one, the formulations. So we have the gradient f, the del f, x, y, z equal lambda, and this is what we call the Lagrange multipliers. Multiply with the gradient g, or the del g, okay? Where the g itself is equal to k, the level curve k. Okay? So from this part, the first part, we are going to get some equations. Okay? So we are going to get some equations.
So this will be this is the Lagrange multipliers. And it will resulting in equations equations in XYZ. Or you could imagine that when we maximize or minimize, when maximize or minimize, the del for f will be parallel with the del of g. Or in our case, the normal line from both of this plane is identical. Okay.
This is why we can equal on these two, because they are intersect, and then we know that they have the same normal line, the identical line.
Okay, I think the important one is how to use this Lagrange. Okay, so I will give you some example. Okay? So let's say we have a function and has constraint so constraint can be anything, can be a plane equation, can be maybe some quadratic surfaces, another quadratic surfaces, it can be anything. So how to find? So find extreme values. Sometimes for some questions you can choose which method you could evaluate. I think the best way to see when we are using the Lagrange multipliers is when we have a function and then we have another function that is going to limit that function. For example, this function is in XYZ, and we also have another seems like an equation that has XYZ that we can simply look at. Okay, if we have this two, it means that the f is our function to be minimized or maximized, right? So this will be something that we need to maximize or minimize. And the other one is our constraint, and the question already mentioned that it has a constraint. So it directly says that, okay, this will be the constraint. So sometimes the question maybe it doesn't really give which one is which. I mean, one function and then the other one just giving another function. It's like this. And then you could tell that, okay, the first one will be the function that we are going to maximize or minimize. The other one is the constraint. So the first thing, to find the extreme value, we can write first that the del of f, or maybe write with blue. So del of f is equal to lambda and then del of g. Okay. which means this can be written at least like partial x equal lambda, another partial x from G, and then partial y, and then lambda. Okay, we can break down all the three components. Okay. From the del f, we can have partial x, y, z for f. For del g, we have partial for gx, gy, gz. Right? So we can have at least three equations. Now our goal in this method is to solve this tree. Either finding the lambda first, or maybe finding some x or y, and then later find the lambda. Anything can happen when we solve this. Okay? So you need to be able to observe and identify how to solve. Okay? Sometimes it will be like a linear equation. Maybe you need to have some method in linear, like substitution, elimination, and so on and so forth. Or maybe you have like polynomials that you need to solve. Okay, it can be anything. Okay? Okay, so first we can write the partial x for f. It will be 6x equal lambda, and then gx will be 3. Okay, so 3. Or let me write 3 lambda, okay, to make it clear. And for partial y, we have 2y equal 2 lambda. And for z, we have negative 4z equal negative 8. So negative 8 lambda. Okay, we can cancel this. And I think we can write all the terms into lambda. So we can write x as lambda. So x will be half lambda, y is equal lambda, and z will be 2 lambda. Okay. And then we can have this all x, y, z in terms of lambda. We can substitute, so we can write here, so sub to constraint. So 3 half lambda plus 2, and then minus 8, this is 2 lambda, and then negative 50. So we can have, this will be negative 16, negative 16 plus 2, 14. Or let me multiply by 2. So this will be 3 lambda plus 4 lambda minus 32 lambda. So 7 minus 32 is negative 25, right? So negative 25 lambda is negative 100, or lambda is 100 over 25, which is 4. Okay. Let me put a little bit to the right side and resize a little bit. Okay. So we have lambda is 4, which means from this lambda we can get x is half lambda or 2, y is lambda or is 4, and z will be 2 lambda, or we have 8. And then this is the extreme value. So extreme value is at f248. And if you want to calculate 248, we can check through the XYZ. So 2 will be that. So 4, 12, 12 plus 16 is 28. 28
64, 128 minus 28 is
negative 100. Negative 100. So we have negative 100. Okay.
so Lagrange can easily find 248. Okay, as long as you can solve this del, you can solve and then find the values for x, y, z. You will be able to find it. You will be able, as long as you can solve the Lagrange equations. Okay? But it didn't tell you whether this 248 is maximum or minimum. It didn't directly tell. So you need to check. Okay? So for example, you check this, and then check another point. Can it be more than that? Okay? I think it can. So we can say that this will be the minimum value. Okay? I think this will be the minimum value.
So this will be the minimum value, which means that the extreme value that we find is minimum. Okay. Okay, and then, for example, let's try to work out the. I think I give you the this question here. Let me copy again. Okay. This one. So the same question. Rectangular box without the top. We are going to make that, and then we have restrictions 12 meters squared for the cardboard. So we are going to make the design, and we want to know what is the maximum volume, or what is the maximum design. Okay, which means we need to find what is x, what is y, what is z to make it maximum. Since the volume is our goal, then we can write, first is writing the volume is x, y, z. So we want to maximize this, okay? Maximize our goal, right? And then we have a constraint 12 meters squared. So based on the area, we have 2xz plus 2yz and then plus xy. Now this is the constraint. This is the constraint. Or if you would like, you could write the first one here, the volume, as the f, and the second one as g. And then using the Lagrange. Okay? You can use the Lagrange also. Okay? So this will be equal to 12. Okay, the constraint. So this will be the constraint. And then the same, we take the del f equal lambda del g. So taking the partial x equal lambda equal gx. So partial x for the volume will be yz, and gx is 2z plus y, 2z plus y. Okay, and then we have partial y. So you can see that
again we kind of have a little bit complicated, but I think it's still we can still do it. So this middle one here, the process, sometimes it can be easy, it can be complicated, okay? And then you could choose like which method you prefer. Okay? Which method you prefer.
And then partial y is xz, and then lambda, and then gy is 2z plus x. Okay, and then the last one is partial z. This is xy. So 2x plus 2y. So to solve this equation, it depends. It depends. It's up to us how we see the equations. For example, we have these three equations. And which one is the best way to solve? Now let's think, we have the tree which has similar structure. We have, the first one is yz, xz, x1. So how about if we multiply this part, we multiply with z. We multiply with x. So it will be x, y, z. The second one, let's say we multiply with y. So it will be x, y, z, x, y, z, and x, y, z. Okay. I think we can do that, and somehow it will be. So let's say we have this will be x, this will be y, and this will be z. So if we multiply, then we have x, y, z. This will be 2xz plus x, y. This is x, y, z. And 2yz plus x, y. And this will be x, y, z. 2xz plus 2yz, right? So we have these three equations now. So equation 1, equation 2, equation 3. Now we need to think clearly what is the possibility we take from these expressions. In general, if we are taking, for example, if lambda is 0, then it's split, right? It's okay. But we need to think when lambda is not 0. So let me write in general, lambda can be 0. But we need to find the other possibility to assume lambda is not 0. Because if we take it 0, then all the terms yz, xz, and xy, it will be 0, and then it will be false because we have this constraint. So we need to assume lambda is not 0. Okay, I think I will continue first, and we can have an early class. I'll finish in I think in a few more examples, and then we are going to end the class. Okay. So basically, we need to assume the lambda is not 0, which means from the let me write, this is equation 1, equation 2, equation 3. So from 1 and 2, we can have 2xz plus xy equal to yz plus xy, which gives 2xz equal to yz, or xz is equal yz. And then since z is not 0, so we can make this x equal y. Again, we need to assume that z is not 0. If z is 0, then the volume will be 0, right? And then from another possibility, from 2 and 3, we can have 2yz plus xy equal to xz plus 2yz. It gives the 2xz is equal xy. And again, since we don't want the sides is 0, so we need to make sure that we write that it's not equal 0. So so then we can cancel, right? We can cancel, and then this will be y is equal to z. Okay. So we have these two expressions, x equal y and y equal to z. So we have x equal y equal to z. Okay. So back to the expression for the g. So let me copy. Copy and then right here. So from this expression, we can then change all x, y with 2z. Okay, so we can exchange that. So we can rewrite so 4z squared, and then this will be plus 4z squared, and then xy will be 2z, and 2z will another 4z squared, and it's equal to 12. So we take all and then solve this z squared. This will be equal to 1. And of course, we are going to exclude the negative because this is a geometric shape. So z will be 1. So x will be 2, y will be 2. So the maximum value is at f 1 to 2, or we multiply x, y, z is 4. So this is the volume that is maximum. So from this 2, we get this expression, and then we can have this, and then this is from the area, right? From the area, the cardboard have 12 meters squared. So we change x with 2z, so it will be 4z squared. Yz, y is 2z, so 2z, 4z squared again. And then last one, xy is 2z, and then another 2z, so 4z squared. So we get a z is 1,
And then from this 1, we get x and y, which is 2z. So 2, 2, 1. Oh, I write wrong.
Should be 2, 2, 1. Okay, should be that.
Okay. So I think for this kind of questions, I believe the first method that we try, maybe it will be more simpler. Right? It's simple than the Lagrange. But the more we have, like for example, if we have like a more complicated one, and if we have two constraints, then Lagrange will be more, I think, preferable. Because Lagrange is basically trying to solve these axiom values, and then it will fit with some constraint. So it works like a machine, like algorithm. So you have the function, and then you will take this function and fit with the constraint. Okay? So it's like working like a machine. Okay? So you have a choices now. If you try to solve the maximum minimum value with Lagrange or with the method that we did before. The way we did before is we find the critical points and then we check the critical points. We can check through the second derivative test, if you remember. So we have partial x, and then we have partial x, we have partial xy, we have partial yy, and then we check with the determinants, the d. Whether it's less than 0, greater than 0. Okay.
And then we can determine which one is minimum or maximum. Okay, let me give you another example. Another example is find points on the sphere x squared plus y squared plus z squared equal 4 that are closest and farthest from 3, 1, negative 1. Now, sometimes the question is giving you something like this.
You have information sphere, and then we need to find the distance, the closest one, and then the farthest one from one point. It means that we need to consider which one is our function, which one is the one that we need to maximize or minimize, and then which one is constraint. I think constraint will be the sphere. The sphere is x squared plus y squared, but z squared is 4. That means it will be the restriction. Which means this question is requiring us to make a function. Okay? And I think the function will be the distance. The distance from the point in the sphere to this point.
So we know that the distance will be d. Let me write d. Distance like that. Based on the point 3, 1, and negative 1, this will be x minus 3 squared plus y minus 1 squared, and then plus z plus 1 squared. And as I mentioned, since this is our approach, modeling the formula, we can simplify the models. So if we think that this square root maybe will be difficult if we try to include that when we compute, then I think we can remove this and take the d squared. Okay, let's make our model in d squared. So let's d squared become our model, or in this case become our function. Okay. So this will be something that we need to maximize or minimize. Okay. And this will be the constraint, the sphere. So we can write the sphere as G. So it is constraint. And then, similar to what we've done before, we take the Lagrange multipliers method. Okay. So we take the partial x. So partial x will be 2x minus 3 lambda, and it will be 2x, so 2x lambda. I think we can solve this. Or so cancel 2. So we have x minus 3, x lambda, and then partial y. So this will be 2y lambda. Again, it will be canceling this part. So y minus 1 is y. Lambda. And the last one, and similarly we get z plus 1 is z lambda. Okay. Now we have this equation that we might simplify, and then since we have the constraint is x, y, z, so somehow we could solve this tree in terms of each x, y, z, right? So we could write down that x minus 3, or I mean write x minus x lambda is equal to 3, or x is 1 minus lambda, or x is 3 over 1 minus lambda. Same thing with y. So we have this x, y, z. Then we can take it to the constraint. So x squared plus y squared plus z squared equal 4. So using this expression, we can write down. So it's a little bit long, but still doable. Okay. So we have 9 I think we can write a very long here, like that. So 9 plus 1 plus 1, right? Squared. So it will be equal to 4. Okay, so from here we get 1 minus lambda squared is 11 over 4. So 1 minus lambda is plus minus square root of 11 over 2. So lambda is 1 plus minus square root of 11 over 2. And then we put back the lambda inside the xyz expressions. So first we can check the lambda 1, which is 1 plus, and then check lambda 2. And then all take to the xyz, each xyz, okay? So this one will become, so the value will be 6 and then another one is negative. So we have these 2 points. And then check the value. This will be the closest. This will be the farthest. Of course, you need to check. Okay, need to check. Check the value lambda 1. This. Check to the functions. This is check to the functions. If it is minimum, it is closest. If maximum, is farthest. So check. I didn't write the value, but you need to check. Okay, one more section just to introduce you where we have 2 constraints, and then we are going to finish the class. Okay. Okay, let's check the another example. Okay, so Lagrange multipliers with a two constraint. So which means that in Lagrange now we have so not only G as our constraint, but also we are introduced to another constraint, which let's say H, and with another symbol of the multipliers, and usually we write as mu, okay? And this will be delta H XYZ. Now of course that we are going to have, based on this expression, we're going to have equation which includes the G and H. Okay. Where the G is equal K and H, let's say, equals C. Okay, I think let me give you just example just to look at. So find max value of F on the curve of intersection of plane x minus y plus z equal 1 and cylinder so this is our function and this is constraint. So these two are constraint. And this is the one that we want to find the max. So first, write del F equal lambda del G plus mu del H. So first we are going to partially derive for x. So all with x, x, and x. So we write in this equation. So with this we have three equations. So partial x, partial y, partial z. And then still, the idea is still the same. We need to solve the equation inside. And then we need to be able to find how to solve that. Sometimes we need to substitute and then solve the all the equations. Okay, so start with the partial x. So fx will be 1. Or let me write here. So let me write g is x minus y plus z, and h is x squared plus y squared. Okay. So gx is also 1, so lambda plus this will be 2x mu, and then this is x, and then partial y. This will be 2. This will be negative lambda, and then plus 2y mu. Okay. And then partial z is, this will be lambda mu, and this will be 3 lambda, and okay, just lambda. So I think the last part here, from the partial z, we get lambda is equal 3. So based on that, we can write this is become 2x mu will be negative 3 plus 1, so negative 2. So x, so we can cancel. X will be negative 1 over mu. And then, so take this 3 to that and that. So this will be negative 3. Negative 3 is 5, so 5, or maybe let me write 2y mu equal 5. Our mu is 5 over, or y. Y is 5 over 2 mu. And then this 2 we can write. In the cylinder we have x squared plus y squared, so x squared plus y squared equal 1. So we can write 1 over mu squared plus 25 over 4 mu squared is equal to 1. So we can write this is 4 mu squared. This will be 29. So mu squared will be 29 over 4. So we have mu is square root 29 over 2, or we have negative square root 29 over 2. And then put back into the x and y this mu, so x will be negative 1, so it will be plus minus, right? Plus minus 2 over square root of 29, and then y also plus minus 5 over square root of 29. And then z is from, so since we have x minus y plus z equal 1, so z is 1 minus minus x and then plus y. So from the x and y we can get z also plus minus, or here is 1, okay, 1 plus minus 7 over square root of 29. So we have x, y, z all with the with each possibility with the positive or negative signs. Okay. And then all these three, we need to check the F. Okay, check the F. At this point,
so we need to check the positive, check the negative, based on So basically, and let me go review what we actually done. So this is partial x, partial y, partial z. From partial z, we get this lambda. We put the lambda back to the equation. We get these two equations here. So we have x and y. We know the constraint from the x squared plus y squared from the cylinder. We are going to equal it to 1. And this is our first constraint, the constraint, the first constraint. We solve, and we get this two possibility for mu, positive and negative. We check the positive one. From here and here, we get some points. We check the negative, and we also get some points, which we have these two possibility, plus and minus. And then from these two possibility or four combinations, we can check through the another constraint, x minus y plus z equal 1. So we can get z. So z also have 1 plus minus. So from x, y, and z, we check again to the x, y, all the points. Okay. So all the points, all the possibilities, check again. Which one is maximum, which one is minimum? If we find the maximum one, that is our maximum value. Okay. So as long as you can solve the middle process here, the last point is check the value. Check the value. So as long as you get here, get solution, then the last point is to check the value. Okay. But your combination will be correct. Your combination will be correct. For example, because we have the negative on x, so when mu is positive, it is negative. But the y is positive. So x negative, y positive, and then z also have another symbol. You need to check. And the combination need to be correct. It need to be correct. So what I mean is, from these two mu's, okay, let me resize this. So at least from these two mu's, we are going to get x1, y1, z1. And from here we get x2, y2, and z2. So we need to compare which combinations can make maximum. Okay, I think that will be will be the end of chapter 14. End of chapter 14, and I think I will just finish up until here. As I mentioned, we might have a quiz, maybe 2 weeks later, around November 30. November 30 quiz will be on chapter 14, partial derivative. I think all sections. Since it's only 1 hour, so I think I will just maybe represent the questions from not each section, maybe just I only take three sections. So maybe only 3 questions. Okay, only 3 questions.